So I came across these wallpaper photos of what I think is a ranger station. Now I was curious where this is, so all I could determine was that it's somewhere in the Atlantic rainforest. But as I continued, I realized more and more that this was going to be one of the hardest challenges I've done. This place is off-grid, meaning there's no address, so no Zillow searches, no tax records, basically no existence of this thing online. It's just a hut in the rainforest. Oh, and this rainforest is about the size of the entire east coast of the United States. But despite all of this, this place is actually findable, and everything you need is on the screen right here. So my first thought was actually to download all of this satellite imagery and then run a Python script to basically match this with each tile here. There are a couple problems with that. One is that this area is just absolutely massive. It would take like 15 terabytes to download this all. The second is that a lot of these remote areas are super grainy. So even if I had the right area and matched it, it just wouldn't match because the resolution's so bad. So while that would have been the simplest thing to do, that idea was pretty quickly out. I've referenced this in a couple past videos, but whenever you're dealing with like a huge search, what's super helpful is to have some sort of data set that you can filter down from. Like in this example, it was tax parcels. Now for this search, what we'd be looking for is probably something like a building data set. Now there's a couple issues with a building data set for this search. The first is that this search area spans multiple states, some of which the size of entire countries. Most of these building data sets are put out by counties for tax reasons, so they're going to be state or even county specific. The next issue is it needs to be exhaustive. The point of using a building data set is so that you can take all the uncertainty of this entire area and collapse it down into one finite list. So if your data set has certain areas with coverage, some without, it's not nearly as helpful. And the last problem is what we're looking for is an off-grid structure. So this building probably won't show up on a data set made for tax reasons. So all in all, I'm looking for a building data set that spans these multiple states, is entirely exhaustive of all buildings, including off-grid structures. And really no data set will check all three boxes. Well, except for maybe one. This is the Google Open Buildings dataset. And what's special about it is that it has building footprints for the entire Earth. So whether that's your neighbor putting up a shed or a hut in sub-Saharan Africa, it'll show up on this dataset. And the reason is because Google runs machine learning algorithms across multiple years of satellite coverage to identify these building footprints. So this doesn't rely on any municipalities or tax records. This is exactly what we need for this search. But you can see it's also not perfect. There are a lot of false positives here and also a lot of missing buildings. But if anything is going to have this building that we're looking for, it's going to be this. So let me download the areas that we're looking at and then I'll flip over to QGIS to show those. All right, now we're in QGIS. We have the buildings in. They're around 45 million in total. Now there's one thing I can do to cut that down a ton, and that's using this top left photo here. It's super remote. There's a few buildings here in this site, but otherwise nothing. So I just made a quick Python script that filters based on the density. So you can see we cut down like 80% of these. So the next thing I wanted to do was match these up with this photo in the top right here, something like this. But you can see in this data set, there's groupings here, and I don't know when this was collected. Maybe only this is there in the data. So that means we can't filter much more just from the building data set itself. So at this point, I had removed all of the high density buildings, but I was still left with just over 1 million in total. But this is where it gets really cool, and this was probably my favorite part of the search. So let's look at a random building here, one of our candidates, and we're looking for this. You can instantly know that this is not the right site. This building is just on a flat slope versus what we're looking for is kind of in a basin here. Now there's actually a lot of information just in this picture. Basically every ridge, valley, dimension can be used as kind of a topographical fingerprint that makes this view pretty much unique. And that's why we're so easily able to look at this and know that it's not the right one. So the question then becomes, how can we do this for the 1 million remaining candidates we have? Well, what Google Maps uses to generate this 3D view is the same thing we already have in QGIS, a DEM. It's basically a grid, and each point on it has some certain elevation value. So if I could kind of make a 3D mock-up of this terrain, then I could check that relative to the terrain around each one of these points. Basically doing what we did here, but mathematically and scalably so that I can do 1 million of them. So to get this sketch, I just used this site. You basically just sculpt it up like it's kind of clay. And I just went back and forth between this picture and the sketch until I got something that looked pretty close. And I'm sure there's more scientific ways to do this, but this is good enough for what we need. So now I need to match this up with the DEM we have, but there are two things I need to solve for first. The first thing, if I'm trying to match this up, I need to know how big this is relative to the DEM in meters. And the second is, what direction is this facing? So I need a scale for how large this is, and then I need cardinal directions as well. The first one's pretty easy. For that, we'll use this top right photo here. We can see a pickup truck, which should be about 5 meters long. My DEM is 30 meter resolution, meaning each 30 by 30 meter square has one elevation value. So I just measured this in terms of 30 meter increments and applied that to the overall view. And again, this doesn't have to be perfect. Like if we're matching this up and it's slightly larger, it'll still get the general terrain. It just might prioritize some candidates that aren't the right one. So that takes care of the scale. The next thing is the orientation. And I think this one was a lot more fun. And for that, I used this bottom photo here. So I've brightened the photo here and you can see we're looking at the same building. Now this kind of band of stars across the sky is actually an arm of the Milky Way galaxy, and it's pretty recognizable, so I'll show you what we can do. I have this night sky simulator here, and it's set to the general region we're looking in. It's important that we're in the southern hemisphere and in Brazil, but you can be 100 miles off and this won't really change. What will change though is the time that you're looking at. So both the time and the month. But you can see there's a pretty small window of time where we're looking upwards at this band like we are here, and it's like actually still dark outside. And more importantly, whenever we're looking, it always shows up in the east. So here's the comparison. You can see we would be looking towards the east, which is exactly what I thought, but I'll show you why that's wrong. Take a note of this star below this band. That star is called Antares, and when we're looking east, it's actually above. It's only as we progress months that it actually flips over and ends up being below here in the west. And so you can see now we have an accurate match looking westward. So again, in that star photo, we were about here looking upwards, which we now know is facing west. So that means this orientation, west is on the left, east is on the right, north, south. All right, so now we have size and we also now have orientation here. So now for each one of these candidates, we take the surrounding DEM and match it versus the sketch, scaled and oriented the correct way. Then the terrains that most closely match our sketch get scored the highest, and we just look from the top down. So that's what this Python code does, and after running it, we just have a list of prioritized sites. So I had it export the top 100 into QGIS, and we can check a couple of these manually. So this one's not it, but you can see it's a lot closer to what we're looking for here. Now, as I kept checking these, I realized a lot of them you can pretty much instantly rule out. Like this one, for example, I'll zoom in here, and I already know this isn't the right one. The reason is because if you look at this picture, these are entirely surrounded by trees. So seeing this area here just instantly disqualifies it. I wanted to make that a bit more scalable, so I added one more filter to the scoring. Basically, what percent of the area directly around it is this dense green foliage. For that, I use this really cool dataset from ESA called World Cover. It's 10 meter resolution, and for each of those 10 by 10 meter squares, it classifies it based on what type of land it is. So I downloaded that, I pulled it into QGIS, and you can see it's super accurate. Basically, what we're looking for is only this dark green. Now, I didn't penalize too heavily for the amount of trees, because you can see even in this photo, there's some areas without tree cover. So I mostly just used it as a way to filter out the ones that were obviously wrong. So now ranking all million-plus buildings based on the terrain match and the tree coverage surrounding. Here is the #1 match. So let's take a look at this in Google Maps. The terrain is a super close match. Again, here's what we're looking for. And it had enough trees to pass the canopy filter, but you can tell this is not the right location. And honestly, that's kind of to be expected. To make it more accurate, I'd probably spend a bit more time on this sketch. But that's also why I scored them and ranked so that I could just work my way down from the top of the list. So it doesn't need to be #1 out of 1.2 million. If it's in the top like 500 or 1,000, that will speed up the search a ton. So I just filtered to like the top 300 rank and then manually checked these, and I'll kind of show you what I do. There's one more thing I noticed while checking these, which is there's a lot of these white trees here, and they show up pretty well on satellite imagery. A lot of the top candidates didn't have these white trees, so I was considering making a script to identify these and then incorporate that into the scoring, but as I kept looking, I pretty quickly found this, which in my opinion looks similar. However, we don't have enough data to 100% confirm. To me, the coolest part of all of this is just how scalable it is. Like both the DEM and the building dataset we used are worldwide, so anywhere in the world this can apply. Imagine in like search and rescue, if you just had a picture of someone with some hills in the background, you could use this to narrow down that location a ton. And this sketch I used is from 15 minutes on some sculpting website, so if you had someone with a lot more experience in 3D modeling, the results would be much more accurate too. But overall, I thought this was a pretty cool proof of concept that even in the absolute wilderness, out of millions of buildings, you can identify where that photo was taken just with the terrain. So yeah, I learned a ton doing this. Hopefully you did as well. That's about it.